Hello. Over the next 15 minutes, I want to talk to you about Himalayan erosion and its links to Neogene global cooling. The idea that chemical weathering of sediment removed from the Himalayas may be driving global climate. So the idea that the solid Earth, especially in Asia, may be having an impact on climate is nothing new. It's well recognized that the uplift of the Tibetan Plateau and the rising of the greater Himalayas may be fundamental in the intensification of the Asian monsoon system. But what I'm talking about here now is more the global climate, and particularly the role that erosion and weathering play in the carbon cycle. So the idea is that bedrocks which are eroded and broken down into sediments may then be affected by chemical weathering, and it is this weathering which results in the conversion of CO2 out of the atmosphere and its precipitation as calcium carbonate in the oceans. And this removal of CO2 from the atmosphere by surface processes is balanced by the outgassing of CO2 both along mid-ocean ridge systems and in oceanic island arcs, which result in a return of CO2 to the atmosphere. This is one of several processes, but these are the dominant ones that we think may be fundamental in controlling long-term trends in global climate. Other features that may be important in this budget is the burial of organic carbon. And in places like the Bengal fan, there's good evidence that organic material exported from the continent by the Ganges-Brahmaputra rivers and affixed to clay minerals. There's this very nice correlation of alumina silica to total organic carbon in the Bengal fan, that this is an efficient way of removing carbon from the continent and burying it, removing it from the atmosphere and burying it in the sedimentary record. And it's not just any old mountain belts which are important in controlling global climate. Francis MacDonald and his colleagues have shown us that the location of the chemical weathering may also be important, that where we have arc and ophiolite rocks exposed in low latitudes, that these are more susceptible to strong chemical weathering, which is reflecting both the faster weathering that is possible in hot, wet, tropical regions, as well as the tendency of more mafic rocks to break down more rapidly and be potentially a primary source of chemical weathering, something that they link to glaciations here in the Ordovician and Carboniferous and Cenozoic, and not so much in the Triassic. So we can understand silicate weathering as being part of a series of processes that can control the carbon in the atmosphere on a variety of timescales. And what we're thinking about today is rather this bottom end, the relatively low fluxes, but operating on very long timescales so that they have a big impact on long-term development of global climate, balancing, as I noted, volcanism, as well as other processes like sulfide oxidation or the weathering of carbonates. And so we test the idea that the silicate weathering of the Himalayas is responsible for drawing down atmospheric CO2 and reducing global temperatures. So this is not a new idea, of course, first proposed by Maureen Ramo and Bill Ruddiman in the early 1990s, and they saw this correspondence between falling global temperatures and changes in the strontium 87-86 ratios in the oceans. And at that time, this was strongly associated with discharge from the Ganges-Brahmaputra River being elevated in this isotope ratio. And so the thought was this changing ocean chemistry was a proxy for Himalayan weathering and erosion, and the fact that it paralleled the falling temperatures was indicative of the control of Himalayan erosion on global climate. And certainly we recognize the fact that atmospheric CO2, measured by a variety of proxies such as boron isotopes, has fallen progressively through the Cenozoic, and that this tracks both the strontium isotopes as well as the global temperatures. So this figure from Christian Franz Lanoud and colleagues from the Bengal Fan make this point rather nicely, showing that CO2 has decreased in the atmosphere since the Eocene, and of course global temperatures have also fallen at the same time that 87-86 has increased. So what I'm going to try and do today is just talk about the Neogene and test the idea that that this uplift of the mountains and their erosion intensifies the chemical weathering, draws down CO2, and results in falling global temperatures. And we do this in a very direct way that has not been possible up until this time. And in particular, we're using data from the Indus, Mekong, and Pearl river systems. And we choose these because they have the benefit both of having sampled the sediments in the offshore depot centers in the Arabian Sea and South China Seas, which allows us to understand the degree of alteration of the sediments. But the other important feature is that these areas are also surveyed by seismic data, and that allows us to derive volumes and therefore mass accumulation rates in cubic kilometers. And that's very important because if we're to generate a CO2 consumption budget, we need to know those volumes. It's not enough just to know how altered the sediments are. The alteration is able to calculate how much CO2 is consumed per unit weight, but in order to generate an integrated flux, we need to know those volumes, which is why we cannot yet consider the Bengal Fan because we don't have the appropriate mass balance. So in the Arabian Sea, we have some nice high-quality industrial-derived data of the continental slope and upper part of the submarine fan, supplemented by 2D lines that cross the entire submarine fan, which allows us to generate a volume for the entire system. And then in this case, there has been drilling on the eastern side of the submarine fan in Laxmi Basin that was completed about 6 years ago at these IODP sites, which allows us to see how weathered the material is. So we use the same method as proposed by Christian Franz Lanoud and Lou Derry in 1997, and this idea is that silicate minerals, when combined with atmospheric CO2 and water, will break down and essentially precipitate as calcium carbonate in the oceans, releasing silica and a little bit of CO2 back to the atmosphere, but consuming one volume. And we can calculate how much CO2 has been consumed by estimating the change in the calcium, magnesium, potassium, and sodium in the sediments compared to their bedrocks. And that means, therefore, that the knowledge of the sediment provenance is also very important. So unlike the Ganges example, we are not really able to use the upper continental crust as a suitable end member for being the starting material, and that's because the sediments themselves in these areas have higher magnesium and potassium aluminum ratios than the fresh bedrock, and that's impossible. So instead we have to estimate what the bedrock might have been before erosion and weathering, and we use proximal sediments both in the large Himalayan tributaries as well as trunk Indus sediments for looking at the rather different, more mafic units in the suture zone in western Himalayas and western Tibet. And in particular, we employ strontium and neodymium isotopes combined with detrital zircon ages to look at how the provenance has changed through time. In this case, a decrease in erosion from the Karakoram and an increase in erosion in the Himalayas, which parallels the changing chemical weather. Likewise, in the Pearl River system in southern China, we are able to use strontium and neodymium to show essentially that the bedrock sources into the South China Sea have been pretty consistently from southern China through time. Again, we have to calibrate our source compositions because of excessive potassium-aluminum ratios compared to the upper continental crust, but this allows us to at least generate a minimum amount of chemical weathering through that approach. And of course, the same sort of thing can be done in the Mekong. The Mekong is slightly more complicated, because the Mekong only appears to have been in its present location since about 8 million years ago. So relatively stable since that time, a more variable provenance prior to that time, with erosion also from Luzon and Palawan Islands, as well as Indochina. But through the use of these isotope proxies, we're able to determine what the evolving provenance was like through time and make an appropriate adjustment. Again, we are able to use an adjusted upper continental crustal estimate to derive a minimum estimate for the amount of chemical weathering. Furthermore, we tested whether these results were robust by also using a totally different approach and instead compiling bedrock data from the GeoRock database in an attempt to see whether using that as the end member composition would have an impact on our results. So this is the result of what we get. This is the Pearl River, Mekong and Indus systems. And you can see the shaded bars here show how the mass accumulation rate has changed through time. The Pearl River and the Indus are higher in the mid-Miocene, then reduce and then increase again in the Pleistocene. It's a little different in the Mekong, probably reflecting drainage capture in this system. You can see from the chemical index of alteration that the weathering is decreasing in the South China Sea through the Neogene. It's pretty flat in the Mekong system and reducing as well through time here in the Arabian Sea, which is of course the opposite of the trend that we would expect if you wanted the greater weathering to be the cause of the cooling seen during this time period. So when we combine these together, you can see that the efficiency of consumption of CO2 is high in the Indus, but doesn't change through time. It's a little bit lower in the Mekong and the Pearl based on our original estimate, the upper continental crustal minimum, again, though not changing through time. It's a little different when we consider the bedrock compositions from GeoRock. This suggests that the Pearl may be more efficient, but still there's no long-term trend in efficiency that we see here. And when we combine this with the deposited volumes, you can see that the Indus, being the biggest system, is the most important, but that its chemical weathering flux is decreasing through the Cenozoic, and in particular, though, just maybe potentially going up in more recent times, but certainly no long-term trend towards higher degrees of CO2 consumption. And the Mekong and the Pearl systems are completely flat. So, essentially, our take-home message is that there is no evidence for increasing chemical weathering flux in the Western Himalayas or the Tibetan Plateau since the early Miocene, and so the long-term trend to colder global temperatures through that time is not related to erosion and weathering in these drainage systems. And therefore, we have to fall back on alternative explanations like organic carbon burial or potentially chemical weathering in other parts of the world, such as the Philippines or New Guinea. We do hasten to add that this does not preclude this mechanism as being more important earlier, maybe during the Paleogene, the earlier stages of orogenesis, but this doesn't appear to be critical in the Neogene. So thank you for your attention, and I'll be happy to take any questions. Thank you.